So continuing on our theme of principles of networking, in this video we're going to describe packet switching. Let me start by saying what packet switching is. So packet switching is based on the switching of individual packets. A packet is a self-contained unit of data that carries with it the information necessary for it to reach its destination. So imagine that I have an end host A and a destination B, and packets are going to flow through a sequence of packet switches in order to go from A to B. So I'm showing an alternative route or path there. And I'm just going to simply call these W, X, Y, and Z. The idea of packet switching is that packets, self-contained units of data, will flow from A to B, and they contain the information, typically in the header, of how to reach B. For example, in one extreme they could have the list W, X, Z, B, telling us exactly how we reach B. Then at each hop we would simply examine the next hop and send it along its way towards its destination. The key here is not whether or not the packet contains the information, it's simply that it contains sufficient information in order to reach its destination, and that it is self-contained in the sense that it doesn't rely on information from a previous packet or from a future packet. There's one common optimization that's used, which is to place the information about the next hop into the packet switches themselves by means of a table that says if your destination is B, then the next hop would be X, so that when this packet arrives at W with eventual destination B, we know that the next hop along the path is to go to X, and X would have a similar state. This is an optimization that is very, very widely used in packet switching, and is used in all of the switches that we're going to see that are in common use in the internet.
So one interesting thing that you might see in this figure, and it shows actually a difference in Nick and my backgrounds, is that you see how Nick put the header of this packet at the front of the packet, because Nick's used to designing routers, and when you're sending a packet from a router, you think about what are the first bits that go out. Well, they're the bits of the header. In contrast, I come from a software background where we think about how is the packet laid out in memory. And generally, you draw computer memory with the low order addresses on the left and the high order addresses on the right, because we write English left to right. And so in these pictures, which is what you'll see in RFCs and other specifications, the header is on the left. And so sometimes it seems confusing, is the header on the left or header on the right? It's always at the beginning of the packet, but just based on our backgrounds from more the hardware and routing side of things and the representations on the wire to the software side of things, we just draw it differently. It's the same thing, and so we hope you don't get confused by that. But the whole point is that even within this discipline, people do have different representations depending on what's important. Like, what are the first bits that are going out of the wire? What do I think about the order on the wire versus, oh, what do I think the order is within memory? So packet switching is a basic principle that's used in data communication networks. This idea of independent data units, which can be individually then routed or directed based on their self-describing state. And so there are really two major consequences of this design. Later in the class we'll talk about other things you can do, like circuit switching or virtual circuit switching, but that's not too important right now. What's important is that the two major benefits that you see from packet switching are, number one, there's no per flow state required. So really, if you're building an enormous network like the internet, you want to minimize the amount of state, the amount of memory the internal switches and routers have to maintain. And because each packet is self-describing or has its own sort of, you know how to route it based on just that packet itself, not prior or future packets, you need to maintain much less state. You don't need to know about these sequence of packets, the prior ones and the later ones. It makes the network simpler, there's less state, and there's less state that can go wrong. And that's seen as a really great benefit for making the network large and robust. The second is that you can efficiently share a link. So because data is broken into these little discrete units, imagine I have a link, and I could start by sending some packets from, say, A to B, but then later I can also send packets from C to D, packets on a completely different pair of nodes to a different destination. And so in this later in time, A and B are not using the link anymore, but I can then statistically multiplex it in time. I can efficiently share it so that many different pairs of communicating nodes can share the resource and it won't sit idle. Because in contrast to other approaches where thinking the most trivial case of, say, a not packet switched network would be that old idea of you take two tin cans and you connect them with a string, right? Where now you have actually a dedicated circuit. If nobody's talking, then the string is unused. But it's only when the people are talking that you can actually use this for communication. In contrast with packet switching, by breaking it up into little chunks of data from all of these different sources and different destinations, you can use the resource more effectively. So just to reiterate, the first benefit is this idea of containing the amount of state which the network has to maintain. You don't need per flow state. It can be that you have some long flow of data from A to B. Say you're downloading a large file or you're watching a long movie. And even though this could be, say, gigabytes or even terabytes in size, the network, all it needs to know is about the packet, right? Where does this next packet go? It doesn't need to know about the past or the future. Now, of course, this doesn't mean that it can't. If we return to the end-to-end argument, it's absolutely valid for maybe the network to try to maintain some state to do things better. Like, I'd like for packets along a flow to generally take the same path for some performance reasons. That's okay. That's an optimization, but it's not necessary for correctness. So the network can do things to try to improve the system, but really the end-to-end behavior of packet delivery does not necessitate per flow state. And because there's no, you don't need state for each flow, you don't need to manage it. You don't need to add it or remove it, worry whether it's up to date or it's stale. You don't need to store it. This reduces the amount of memory which your internal systems need or require. Of course, you can use memory again for optimizations, but again, you don't need to have state in every router for every single TCP flow that's passing through them. Doing so is exorbitantly expensive. And finally, if you're maintaining this per flow state, one of the issues that really comes up as your network grows bigger is nodes fail. A router goes down, a link goes down, a backhoe severs an optical link. And if you're not maintaining this per flow state, then suddenly when there's a sudden shift in the network, you don't need to repair it. You don't need to change it because, gosh, I can just route around it. And it's, again, just based on these individual packets. I'm just making decisions for the next hop based on the packet itself.
The second major consequence that Phil mentioned was that with packet switching, we can use links, we can share them more efficiently. So data traffic is bursty. Whenever we're communicating over the internet, then we tend to be talking in bursts. When we're downloading a web page, we're sending email, we're typing. Those communications tend to be very bursty. We pause and think between the different operations, or if you're a slow typer like me, then there's a long time between each character. So because of this bursty nature of the communication, it would be very inefficient to pre-reserve or pre-dedicate the capacity of each link for each flow. Because if we were to do so, most of the time it wouldn't be used. So if we reserved a fraction of the link for each flow, the links would be used very inefficiently. Packet switching allows us to use those flows use that link capacity much more efficiently. And this is a characteristic that we call statistical multiplexing. So if I have two flows coming in on two links, so this is a sequence of packets coming in on these two links, and they're coming into a router, which I'm just going to draw as a multiplexer here. If I was to pre-reserve the capacity on the outgoing link, let me put numbers here just to show the flow that they belong to, then I would have to pre-reserve a fraction of the capacity. Maybe I alternate between these two, 1, 2. But if at one time this flow number 1 didn't have anything to send, I would actually have a gap here that wouldn't be possible to use. With packet switching, it allows 2, in this case, to be able to fill in that unused capacity and use that slot so that we can use all of the capacity of this outgoing link. As a consequence, we get more efficient use. It's always used when there are packets to send. And this benefit we call the statistical multiplexing gain that comes from using packet switching.
So this is different than, say, how you think a normal voice call works. If I pick up like an old-fashioned phone, when I pick up my phone, there's a copper wire going to the PSTN, the public switch telephone network. And I use that wire the entire time the phone is up, whether or not I'm speaking, even if there's silence. Now, of course, behind that, it used to be you'd actually connect these wires and they would be idle for most of the time. Behind that today, you actually take your voice traffic and turn it into IP and packets because you get statistical multiplexing of all the backbone telephone links. But that's an example of something which doesn't use packet switching and which doesn't benefit from statistical multiplexing, like your simple twisted copper pair phone line. Now, one other thing is that while individual flows tend to be bursty, you request a web page, you get a response. You say something on your Skype call, and then there's a pause, and then somebody says something back. It turns out that in aggregate, much of this burstiness can wash out, such that if you take 1,000 flows and you aggregate them, over time, their traffic is much smoother than any individual flow. And so this is one of the reasons why you can use the statistical multiplexing to get better utilization, in the sense that when you start pulling many, many flows together, some of them might need a link for a very short period of time for their burst, and in aggregate, you can actually sustain a reasonable utilization and capacity use of the resource.